Welcome to this lecture session recorded from home during the time of coronavirus outbreak. The topic of this session is ECS, Entity Component System, a completely new programming paradigm introduced to Unity from the version 2018.2. This is basically replacing a traditional processing and computing model based on game objects and mono-behavior class with something that is significantly more efficient. ECS is about separation of entities, data components, and behavior or logic represented by systems. You might think that entity is something a bit like old-style game objects in Unity, but nothing could be more wrong than that. The focus in the ECS architecture is entirely on the data components, and to be more precise, on the data streams composed of these data components. In this diagram here, you can see a number of data components that form two input and one output streams of data. The input is consumed and the output is produced by the system. The system that represents the behavior or logic of the game. But the important point is that this system is independent, or it works externally from any entities. You have a number of entities here, a number of data components, and one system that just takes the stream or several streams of input data, do some basic calculation. In this case, this system combines translation and rotation to produce the combined local to world transformation. And this transformation produces the output stream sent to another component data. Component data are just pure data. There's no logic, no code in these components here, just data, variables, float numbers, vectors, matrices maybe, but it's just data. System does all the processing, okay? So it's you might say it's not object-oriented processing, because the process obtains or gets a collection of data components coming from a number of entities and does all the processing in a for each iteration. And then we have the final question: what are the entities then? Entities are just like labels, or IDs, something that groups a number of components together to tell that these components, for example, these four components here, describe a single, well, entity. But this entity cannot be thought like that it is something like a game object if it has no internal logic, if all logic for the entity is external, represented by this system. Moreover, with a single entities, you can have many systems working on collections of data components coming from a number of entities. Each entity can differ in the range or combination of specific data components, and such a combination of a unique combination of components is called archetype. So you can notice that in our diagram we have two different archetypes. One archetype contains four components: translation, rotation, local to world, and renderer. And the second archetype is similar, but it does not contain renderer. For a system which we saw in the previous slide, both of these archetypes are good because this system only produced translation, rotation, it consumed translation, rotation, and produced local to world. We can imagine another system, perhaps, which takes data stored in the renderer components, and the renderer components contains data like a mesh and a textural material. Okay, so a mesh and material, and there may be another system that uses these data just to, why not, render an object or render a visual representation of an entity. So far we know that one important part of the system are data components. These data components are organized into entities. Then let's call it families of entities with the same combination of components are called archetypes. And then we have this thing that is called a system, which will just do some kind of processing one by one by one by one for each component in each entity that fits to some kind of pattern. And there is one more important thing, the archetype of an entity determines where the components of this entity are stored. So everything in a single archetype is stored in a continuous chunk of memory. If it gets full, then another chunk will be created. But what's important, if you access a collection of entities represented by a single archetype, its memory, its data components will be stored together. And this is a very significant memory optimization that makes operations on chunks of entities much faster. And this is one of the many things that makes the ECS so fast. It's not just this thing, but one of the many things that makes the ECS so fast. Of course, the other thing is that all the processing, just imagine that we have here a single iteration that just goes along a number of entities and data components from these entities, rather than calling update function of one game object, update function of another object, another game update function of yet another object. It's just faster. Okay, so this is the big idea behind the ECS system in making games more efficient, in making games faster. There is not too much programming for the EC part of the ECS. You need to create your entities, and this process is relatively straightforward. And you need to create your data components, but these are extremely simple struct, C# struct definitions, so also nothing complex to do. The main thing in ECS programming is to implement the systems, or the S, in the ECS. Unlike programming with traditional game objects, the systems deal with entire series of entities. Typically, an action will execute a for each iteration using something that is called an entity query, and you can see an example here. It is built as a function call of an object called entities, that is a collection of all the entities in the system, and the function name is for each, and this function takes a lambda function. This is a little bit funny C# syntax here, but anyway, what it does, it chooses all the entities that are compatible to this signature, which in this case it's every entity that contains translation data component and move data component. So this is basically a definition of a entity archetype. So it will take each entity that is compatible with this archetype definition and will do some action with this in a very fast-going iteration. In this case, it will take the z component of the value of the translation, and it subtracts the move component value multiplied by delta time. So this is basically moving the object along the z coordinate towards the camera. So that's a very simple animation. So an action in the system is applied for each entity in a given archetype or several archetypes, fed by a data stream coming from a single memory chunk or a few memory chunks in a quick burst of calculations. And this way in which multiple entities or the data components are processed by a fast system working for each iteration, this is exactly what makes ECS so fast. So what could make ECS even faster? There is a way to do it. It's called C# job system. It's a special set of additional classes and tools or APIs that make the organization of the entity query we saw in the previous slide even faster, even more optimized through the proper use of multi-core architecture of modern processors. To make the full use of C# job system, there is a special new version of a compiler called burst compiler that can generate these very fast bursts of processing in which consecutive data components are just very quickly. So this is the way to make ECS sometimes even 10 or 20 times faster. But these C# job systems are outside of the scope of at least this introductory part of this lecture. And now it is time for a demo.